Number 1 is from chapter 3. We won't do that on our test in Janice class. The answer is z-score. The set of all possible outcomes of an experiment is called the sample space. In probability, we use the number of items in a sample space quite a bit. The probability of an event can be any number between and including 0 and 1. 0 means the event will not happen. 1 means it certainly will happen, like a 100% chance of it happening. Probabilities can be any number in between that, any decimal or fraction that falls in between 0 and 1. No negative numbers, no numbers bigger than 1. The number of permutations of n objects all taken together, so there's n objects and n slots to put them in, is n factorial, or the same thing would be a permutation with n objects and n slots to put them in. The sum of all the probabilities of the events in the sample space is 1. If you add up the probabilities of everything in your sample space, you should get 1. There are 3 kinds of probability: classical, empirical, subjective. Subjective is an expert's opinion. Empirical is that which relates to doing an experiment. Classical means when you figure out what should happen by taking the probability of what should happen. So in blank probability, all outcomes in the sample space are equally likely, classical. Blank probability uses a frequency distribution to compute probabilities. So that would be in an experiment, so that's empirical. A meteorologist is an expert, so that would be subjective. Determine whether something is mutually exclusive. Mutually exclusive means that they can't happen at the same time. So rolling a die, getting a number greater than 3, well, that would be 4, 5, or 6. Getting a number less than 3, that would be 1 or 2. Those don't happen at the same time. So yes, this is mutually exclusive. Roll a die, get an even number, that's 2, 4, 6. Get a number less than 3, that's 1 or 2. Those could happen at the same time. You see 2 is on both lists, so this is not mutually exclusive. Dependent means that one outcome influences the other. Tossing a coin, drawing a card from a deck. Those are independent events. Doesn't matter what happens in tossing a coin, will have no impact on drawing a card from a deck. Without replacement, or not replacing a ball, that is dependent. That will change the sample size if you don't replace the ball, so that's dependent. Number 5 won't be covered in my class. I've put the answer there if you need it. The complement of, so the complement means not. So guessing 5 correct answers. So guessing 5 correct answers, that's like getting correct, 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 correct. What's the opposite of that? What is not that? I started to make a list. You could have 1 wrong, I put N for not correct, and it could be in any of those spots. You could have 2 wrong that would happen in a bunch of spots. You could have 3 wrong that would happen in a bunch of spots. You could have 4 wrong. I stopped making my list. So let's see. The complement's going to be all these options. So guessing 5 incorrect. Nope, that is part of the complement. One of my choices would be 5 incorrect, but it's all of this stuff, so that's not right. Guessing at least 1 incorrect answer. That's it. That's this. At least 1 means 1 or above. That is the complement of getting 5 correct answers. How many ways would there be to answer this exam? So count up how many different ways you could do this. Well, let's see. There would be 2 ways to answer the first question, and then, so times, 2 ways to answer the second question, and then 2 ways to answer the third question, and so on. So 2 to the 5th power, 32 ways to answer this question. When a card is drawn from a deck, find the probability of getting these things. First thing, sample space. 1 card. We're only looking at 1 card. So the number of items in our sample space is going to be 52. There's 52 cards in a deck. When doing this problem, I would have my green formula sheet out and be looking at the sample space, looking at the deck of cards, the list of the deck of cards. It's probability of getting a heart. You count up, there are 13 hearts out of a total of 52 cards, 13 out of 52, which reduces to 1/4. A 5 or a heart. Okay, well, or means add, so you have to add the probabilities. A 5, how many 5s are there? Well, there's 4 of them out of a total of 52. How many hearts are there? 13. But now, these are not mutually exclusive. It means you could have a 5 and a heart at the same time. So you have to subtract off the things that could happen at the same time, the 5 of hearts. That's the probability of getting the 5 of hearts is 1. There's 1 item in the overlap. C, a 5 of hearts. There's only 1 5 of hearts out of a total of 52. There's your probability. A red 5. Look at your sample space. How many red 5s are there? 2 out of a total of 52 cards. So that's 1/26. A red card. Half the cards are red. Or you can count them up. There's 26 red cards out of a total of 52. Or you may just know that that reduces to 1/2. Half the cards are red. The probability of an event happening is 0.42. What's the probability that the event won't happen? We would show it like this, the probability of its complement. Complement is 1 minus that probability. You'd subtract it from 1 or subtract it from 100%. 0.58 is the probability that event will happen. 9 through 12 are calculator problems. I've put the answers here. How many different ways can 8 kindergarten children be seated in a row? Well, does this repeat? No. You can't going to repeat kids if you're sitting them in a row. And does order matter? Yes. I'm talking about how many ways I can order them. So yes, order matters. So you could do this 2 different ways. You could use permutations and say, how many kids do you have to choose from? 8. How many slots are you seating them in? 8. All 8 of them are going in the row. 8p8. Or you could say, all right, I've got 8 seats. How many choices for the first seat? 8 kids. So now I used a kid. How many choices for the second seat? 7. And so on. Or 8 factorial. 8 factorial and 8p8 are both the same thing. They turn out to be 40,320. A beachfront candy store allows customers to select 3 different candies to be packaged and mailed. If there are 10 varieties available, how many possible selections can be made? Do these repeat? No. You're going to choose 3 different candies. Does order matter? No, you're putting them all in a box. It doesn't matter in what order you place them in the box. So that's going to be combinations. Okay, first number. How many total candies are you choosing from? 10. How many slots? How many candies are you putting in the box? 3. So 10C3 on your calculator, 120. One company's ID card consists of 5 letters followed by 2 digits. How many cards can be made if repetitions are allowed? So you are repeating, so we don't need to talk about order right now. So I like to do this with just slots. I have 5 letters and 2 digits. So how many choices for that first letter? 26 letters in the alphabet. Repetitions are allowed. So there's 26 choices for each letter. So 26 for the first, and then 26 for the second, and so on. And then your digits, there's 10 choices for a digit. That's one way to think of it. You could also think of it as 5 letters, choosing 5 letters, and then, so multiplied by choosing 2 digits. Since they can repeat, this is going to be 26 to the 5th power times 10 to the 2nd power. So either way, that's a 6. Either way of doing that gives you this really big number. I'll write it out. Total choices. Repetition's not allowed. So they're not allowed, and yeah, order matters. So again, 2 ways to think of this problem. Letters for the first 5 spaces, so that's 26. You can't repeat, so now there's 25 choices for the next one, and so on. And then how many choices for your digits? 10 choices for the first digit, no repetition, so and then 9 choices for the next digit. The other way to think of it would be, again, get your 5 letters and then get your 2 digits. So how many choices for your letters? No repetitions, order matters, that's permutations. So to choose the first 5 letters, there's 26 P5, 5 slots that you're putting 26 letters into. And then choose your digits. There are 10 digits you're putting into 2 slots. So either way will give you this big number for the total number of ways to do this. How many ways can 5 sopranos and 4 altos be selected from 7 sopranos and 9 altos? So we're going to think of it as doing your sopranos and then your altos. So sopranos, let's see. Can you repeat? No, you're not going to pick the same person twice. You have to pick different people, so no repetitions. Does order matter? No, we're not assigning them rank or anything, so all I have to do is just pick a group of them. So that's going to be C. So first I'll pick the sopranos. There's 7 total sopranos that I'm filling into 5 slots. So 7C5 times the ways to choose the altos. Again, combinations. There are 9 total altos, and I'm picking 4 spots for them to be in. So 7C5, which is 21, times 9C4, which is 126, 2,646. A single die is rolled 4 times. Find the probability of getting at least 1 5. First thing, I a lot of times for these dice problems use the sample space sheet on my green sheet, my formula sheet, but that one is for a specific problem if you roll 2 dice at a time. So it won't really help me here. So let's see. A single die is rolled 4 times. Find the probability of getting at least 1 5. First, what's the probability of getting a 5? 1 out of 6 on a standard die. So what's the probability of getting not 5? 5 out of 6. Another way to write that would have been the complement of getting a 5. So the probability of the complement of getting a 5. This is a hard probability to figure out, so we use an easier probability to find at least. To find at least, we find the probability of getting no 5s and then subtract that from 1. The probability of getting no 5s is the probability of getting not a 5 and then getting not a 5 again, and so on. So not getting a 5 and then not a 5 and then not a 5 and then not a 5. 5 6 times 5 6 times 5 6 times 5 6 is 0.488. No, 0.483. So that's the probability of getting no 5s. So getting at least one 5, that's the complement of getting no 5s. So I just do 1 minus 0.483, and I get 0.5177. My rounding's off there a bit. Four cards are drawn from an ordinary deck without replacement. Find the probability of getting all diamonds. The key word here is without replacement. If you don't replace the cards, it changes the next probability. So you want to find the probability that the first one is a diamond. That would be 13 out of 52. And then the second one is a diamond given the first one was. So let's see, you took out one of the diamonds, so now there's 12 left, and you took out one of the cards, now there's only 51 cards in your sample space. And then on the third draw, again, assume that you got a diamond. So now there's 11 left, and there's 50 cards left, and then 10 out of 49. Squiggly equals means approximately equal to 0.003. Without replacement, all aces. There are 4 aces out of a total of 52 cards. So the probability of drawing the first ace would be 4 out of 52. You don't replace it. So then the probability of getting the next ace would be 3 out of 51 times 2 out of 50 times 1 out of 49. You can see just by looking that this is really unlikely. That you draw all the aces, don't put them back, and you just draw out all 4 aces. That would be really lucky. Here's how lucky. 0.000037. What about all aces with 5 cards? So 4 aces with 5 cards drawn without replacement. The probability of that is 0. You can't get aces on all 5 cards if you don't replace them, because if you got aces on the first 4, you took out all the aces, you can't get an ace on the last one. So that probability would be 0. 4 cards are drawn from an ordinary deck with replacement, so now they are replaced. Find the probability of getting all diamonds. The probability of the first card being a diamond would be 13 out of 52. Since I replace it, I still have 13 diamonds in the deck, and I still have 52 cards in the deck for each of my 4 draws. That's a 9. Probability of getting all aces. Well, the first card, the probability of getting an ace is 4 out of 52. Since I replace it, my probability is that same number each time. So the probability of the first one being an ace, and then the second one is an ace, and then the third one is an ace, and then the fourth one is an ace. Still unlikely, but a little bit better than if I don't replace them. What about all aces with 5 cards drawn with replacement? Now this is possible because you could get 4 aces, a chance of 4 out of 52 for the first one, and then 4 out of 52 for the second one, and then 4 out of 52 for the third, all the way 5 choices. So that number to the 5th. You can do that out in your calculator. Draw a tree diagram for tossing a coin 3 times. Well, the first draw, you're going to have a head or a tail. That'd be here, head or tail. And then after that, after this head, you could get a head or a tail. Or if you got a tail, then you'd get a head or a tail. And then depending on those, you could get a head or a tail or a head or a tail on each of those choices. So you could get a head, head, head. Or if I follow out to this branch, that would be getting a head, head, tail. Or if I followed this branch, that'd be head, tail, head. And so on. So find the total number of outcomes. There's 8 total outcomes there. Find the probability of getting tail, tail, tail. Well, what's the probability of getting that first tail? A half. How about get this flip? That's also a half. You're going to get a head or a tail there. And this flip is also a head or a tail. So this is a half times a half times a half, an eighth. You can also get that by saying, okay, each of these are equally likely. There's 8 choices, so the probability for getting one of these is 1/8. So the probability here is 1/8. The probability of getting a head, head, head is also 1/8. So the probability of getting tail, 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 or means add, head, 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 would be 2/8 or 1/4. When I start a problem like this with a table, I like to total things up. So I like to figure out how many total high school grads there were by adding the amount that attended and didn't attend sporting events. I like to add up how many total 2-year grads are there, how many total 4-year grads are there. Also, what was the total of people that attended games? So add those numbers. And how many total didn't attend? Add the bottom row. And then by adding both of these numbers or both of these numbers, I should get my total number of my sample space, which is 116. That's the total number in my sample space. So, first question. If an employee is selected at random, find the probability that the employee is a high school grad or a 2-year grad. Okay, so a high school grad or a 2-year grad. Notice, no overlap there. So I can just add together those probabilities. We would call those mutually exclusive events. So 28, the total number of high school grads out of the total number in our sample space, 116, plus 39 people that are 2-year grads out of our total of 116. So that gives us 67 out of 116 that fall into high school grad or 2-year grad. The employee is a high school grad or attends sports events regularly. I think there's going to be some overlap there. That is not mutually exclusive. So a high school grad or attended sports events regularly. So you can do it 2 ways. You can either add up these 4 numbers, or you can add up your high school grads, so that's 28 out of 116, plus your attending sports events, 60, and then subtract off that part that you just counted twice. Subtract off the overlap. Subtract off 16. So that is going to be 72 out of 116, which reduces to 18/29. Given that the employee is a high school graduate, he or she does not attend sports games regularly. Okay? So that you want to know the probability of not attending given that they're a high school graduate. So what that does is it just reduces your sample space to only talk about high school graduates, given that they're a high school grad. Okay, well that sample space is going to be 28. There's only 28 people that were high school grads. So given that, what's the probability that they didn't attend? 12 of those people didn't attend. So 12 out of 28, or 3/7. Here we're going to combine some of our counting rules with what we know about probability. On a lunch counter, there are 3 oranges, 5 apples, and 2 bananas. If 3 pieces of fruit are selected, Find the probability that 1 orange, 1 apple, and 1 banana are selected. First thing, let's figure out how many items are in our sample space. How many ways could you choose 3 pieces of fruit from those fruits altogether? Not given that it's 1 orange, 1 apple, and 1 banana. What's in our sample space? Well, that's a combination. We don't care in what order things are selected. And how many pieces of fruit do we have altogether? Let's see, 3 and 5 and 2. That's 10 pieces of fruit altogether. And we're picking 3 pieces of fruit, so there's 3 slots that we're choosing. So 10C3, that would be how many choices there are for picking 3 pieces of fruit out of that pile of fruit. So that's how many in our sample space. Now we have to count up the number of ways there are to do this, to get 1 apple, 1 orange, and 1 banana. Well, let's see. There's 3 oranges, so there's 3 ways to get an orange, and then there's 5 ways to get an apple, and then there's 2 ways to get a banana. So there are 30 ways to get 1 orange, 1 apple, and 1 banana. There are 120 ways that you could pick 3 pieces of fruit. So your probability is 30 over 120, or 1/4. Also, in Connie's notes, she did it with combinations. There are 3 ways to choose that, or no, 3 oranges, one way to select that, 1 slot to select that in, times a combination for the apples, 5 apples to choose from, you're picking 1. And bananas, 2 bananas, and you're picking 1. That turns out to be 3, 5, and 2 over, just like we did, 10C3. Same answer. I find the best way to do this problem, to organize it for myself, is to use a tree. You would not have to use a tree, but I think it makes the organization simpler. Okay? So you have a bunch of people, and some get vaccinated and some don't. Right? 25% of those people get vaccinated. So that's 0.25 chance that they're going to get vaccinated, and a 0.75 then that they don't get vaccinated. So then of those people, the vaccine is 90% effective. So that means in people that have the vaccine, 90% of them will not get the disease. So how many are going to get the disease then? 10%, 0.1. So how about if you're not vaccinated? If you're not vaccinated, you'll get the disease 50% of the time. So if you're not vaccinated, 50% will get the disease, 50% won't. So here, this guy right here, this is vaccinated and then gets the disease. So 0.25 times 0.1. This tree, vaccinated and no disease, is going to be vaccinated 25% and then 90%, 0.25 times 0.9. Not vaccinated and then get the disease is not vaccinated, 0.75, and then get the disease times 0.5. And not vaccinated and no disease is 0.75 times 0.5 again, 0.375. Again, this is everything in our sample space. So when I add these numbers, I should get 1 or 100%. This is 100% of what could happen. So now we want to know if a person is selected at random, find the probability that he will contract the disease. So which of these have the disease? These people got vaccinated and have the disease, and these people didn't get vaccinated and have the disease. So this one or this one. Since it's or, we're going to add those two together, and we come up with 0.4. You could do this without the tree, but I think the tree makes it easier to follow. Draw a tree diagram. Well, the first choice you get to make is if you're going to do beef, pork, chicken, or veal. After that, each one of those will branch off. Each one you have a choice of getting baked or mashed potatoes. And then after that, each one of those choices, so you've got 1, 2, 3, 4, 5, 6, 7, 8 choices. Each of them, you get to choose peas or green beans. So if you add all those up, that's 16 different outcomes, 16 items in my sample space. The way to do that without a tree would be to say you've got 4 choices for your meat, and then you've got 2 choices for your potato, and then you've got 2 choices for your veggie. 16 outcomes. Before I start this problem, I like to figure out what my sample space is going to be. Actually, not what my sample space is, but the number of things in my sample space. The number of things in my sample space, I just count up all my dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 things altogether there. 14 dots. So first thing, what's the probability that I am in circle A? Notice it doesn't say just A, the whole circle A. So you can see in the pink there that there are 5 dots out of a total of 14, 5/14ths. So probability that I am in B. Well, I have highlighted circle B. How many dots are in that circle? 2, 4, 6. So that's going to be 6 out of a total of 14, which reduces to 3/7. 3/7 chance you're in B. Probability of the complement of A. Well, complement of A is 1 minus the probability that you're in A. So 9/14. Or you could look at it on the picture. Where are the spots that aren't in A? Well, here and here. That's not A, right? How many dots there? 2, 4, 6, 8, 9. There are 9 dots, 9 out of 14, like we had, 9/14. Probability of being in A or B. That's this picture. You're in A, or you're in B, or you're in both. It's that picture right there, A or B. So how many dots are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 out of a total of 14, 9/14. A and B. A and B, where's that? It's the overlap part. It's the part that are in both circle A and circle B, which is just 2 items, so 2 out of 14, 2/14, which will reduce to 1/7. Last one, probability that you're in B, circle B, given that you're in circle A. So what that does is, the given that you're in circle A just reduces our sample space just to circle A. So we're just looking at the part that's highlighted in brown. So what's the probability that you're in circle B given that you're in the brown area? Well, there's 2 people that are in B that are in that brown area. So there will be 2 people out of that reduced sample space of 5. So 2/5.